Hello and welcome to this tutorial on the Fibonacci numbers. This is a popular sequence of numbers, and in many basic programming courses it is used as an example to show the principles about recursive functions. However, the kind of implementation that is used in a lot of those courses has a bad performance, and we are going to discuss why. Also, I will show you how to implement a function that calculates the Fibonacci numbers recursively in a more performant way. The Fibonacci numbers are a sequence of integers, and actually there exist two definitions, the modern one and the more traditional one. We are going to use the modern definition, but basically there's not much difference. So by the modern definition, the Fibonacci numbers are 0 and 1 by definition, and then every following Fibonacci number is just the sum of the two preceding ones. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on and so forth. So to speak more formal, if f denotes the Fibonacci numbers, so f of 0 is 0, f of 1 is 1, that's by definition, and then every Fibonacci number where n is greater than 1, the nth Fibonacci number is just the sum of the two preceding ones, f of n minus 1 plus f of n minus 2. Okay, so we want to code a function fib of n that should return 0 if n is equal to 1, it should return 1 if n is equal to 2, and otherwise it should return the sum of the two preceding numbers, which is just fib of n minus 1 plus fib of n minus 2, alright? Notice that we have two base cases here, or two trivial cases, and we have one non-trivial case. Also, for the sake of simplicity, you can assume that n is greater than 0 when you call the function. Again, in a real-world application you would have to check that. So why don't you take a minute, pause the video here, code that function in your favorite language, and when you're ready you can resume the video. Welcome back, I hope you found the solution. So if n is equal to 1, we want to return 0, else if n is equal to 2, we want to return 1, else we want to return the sum of the two preceding numbers, alright, which is this. And to test it, we are going to right line fib of 5, because the fifth Fibonacci number is 1, 2, 3, 4, 5 is 3, okay? So this is session number 2, load file, and 3. How about the 15th Fibonacci number? It's 377. What about the 45th Fibonacci number? Well, this takes some time, and this is why this function is a bad solution, because it is not performant. Alright. Actually, I can show you how long it takes on my machine, because I've prepared a function for you, measure time, that takes a function as an argument. If you don't understand what's going on here, don't care about it. We are going to just measure the time of the code that is written here. Okay. So we wanna measure the time. We wanna measure how long does it take to calculate the 45th Fibonacci number. All right. So let's try it out. It's about 5 or 6 seconds. Okay, execution time 6.1 seconds. So this is quite a lot. Okay, so what's going on here? I'm going to use the substitution model to substitute the call of fib of 5. Okay, so fib of 5 is going to be reduced to this one here, which is fib of 5 minus 1, which is 4, plus fib of 5 minus 2, which is 3. Fib of 4 is reduced to fib of 3 plus fib of 2, alright, plus fib of 3 is reduced to fib of 2 plus fib of 1. Okay. Fib of 3 is reduced to fib of 2 plus fib of 1. Fib of 2 is reduced to 1 directly. Fib of 2 is reduced to 1 directly. Fib of 1 is reduced to 0. fib of 2 is reduced to 1, fib of 1 is reduced to 0, plus 1, plus 1, plus 0, okay? So we get this just using the substitution model. If you don't know what the substitution model is, you can watch the first video I made about the introduction to recursion, but it should be clear by now actually. So what's going wrong here? You can see that we calculate, for example, the second Fibonacci number 3 times, okay? We calculate the third Fibonacci number 2 times, and we also calculate the first Fibonacci number 2 times, okay? So what we are doing here is redundant computation. We forget the stuff we already calculated, okay? And we calculate it over and over and over again. So we do lots of redundant computation, and this is ruining our performance. I'm going to show you this in another example. So this is an article of MIT. It's very old. It's from the 80s. So computer scientists know about this problem for a long time, and they call it tree recursion because when you draw this in a more distant way, what you receive is something like this graphic here, okay? So this is just a thing we did. So they also used the substitution model to split up or to analyze what the function does, okay? So we can also observe here that, for example, the second Fibonacci number is calculated 1, 2, 3 times, okay? And if you already know what a tree is in computer sciences, you will notice that this looks like a tree. In fact, this is a tree, and this is why this behavior is called tree recursion. So tree recursion in that way is always prone to redundant computation, okay? And this is the problem. This is why the performance is so bad. They even call it a terrible way to compute the Fibonacci numbers. Okay, so let's try a different approach. So I'm going to write a function. I'll call it fib2, and actually this will look almost the same like this, but with a little change here, okay? What I'm going to do is I will write myself a helper function, okay? A helper function, and I'll call this fib2 inner, alright? And I'm going to call this helper function here, okay? And the algorithm I'm showing to you is an iterative algorithm. So we are going to do iteration. Yes, we are going to do iteration without loops. We're going to do iteration with recursion. Alright? You can do iterative algorithms with recursion. So, as it is an iterative algorithm, we are going to use an iteration variable. In our case, it's not exactly a variable, but it will be a parameter. So we're going to have an iter parameter, and we're going to memorize the previous Fibonacci number. Okay, so this is the Fibonacci number of the iteration with the index iter minus 1. Okay, and we're going to memorize the number before the previous Fibonacci number. I'll call it ppref. Okay, so in every iteration, the iterative Fibonacci number is the sum of the two previous Fibonacci numbers. Okay, yeah, that's it. So how does it look like? So we have a kind of end criteria, iteration ending criteria, which is for us something like a base case or a trivial case, and this is when iter equals n. Okay, so when we do the nth iteration, we are done. Okay, we are done, and we have to return the iterative Fibonacci number, which is just pref plus ppref. Okay, this is our trivial case. Otherwise, we're going to return, we're going to step into the next iteration. Okay, so in the next iteration we're going to call this function again. So this is our loop header, if you want to. Alright, this is something like our loop. And what arguments are we giving to the next iteration? Well, n stays the same all the time. Okay, for iter, well, we have the next iteration, so we better increase the value by 1. In the next iteration, the previous Fibonacci number will be the iterative Fibonacci number, which is pref plus prepref. Okay, and the Fibonacci number before the previous Fibonacci number in the next iteration is the previous Fibonacci number in the current iteration. Okay, so this call is a little bit tricky. This is where the magic happens, so to say. Think it through. Okay, you can even pause the video or watch the video again, watch this part again. So this is the important part. Okay, this is where all the stuff happens. So we have just one task left. How are we calling this function initially? So obviously n will be n. Okay, we want to calculate the nth Fibonacci number, and we're going to start with the third iteration because we already have the cases of n equals 1 and n equals 2 covered here. So why not start with the third iteration? Okay, the previous Fibonacci number will be the second Fibonacci number in the initial call, which is just 1. Okay, and the previous Fibonacci number will be 0. All right, it's the 0 here. Okay, so we're done, and now let's try it out. Right line, fib2 of 5. That should be 3. Okay, so let's try it out. Load file 3. Let's try it out with a value of 45. Oh wow, it works. Let's try it with an even bigger value, like 450. Alright, it's a pretty huge number, but the calculation was very fast. Actually, we can measure the time here again. Measure time, one iteration, and yeah, why not calling fib2 of 45 or 450 to make things more funny. Okay, more fun. Load file. Okay, execution time 0 seconds. So this is pretty fast actually, and yeah, so this is a faster way to implement the Fibonacci numbers. It's an iterative algorithm. You do not need loops to do iterative algorithms. It's also possible we are using recursion. Actually, I want to show you one more thing. This is a JavaScript thing. It doesn't work in every programming language, but it works in JavaScript, and it is a very nice way to organize your code, and I'm going to show you that. You can actually place this helper function inside the function where you need it. Okay, and you can access in this helper function, you can access the parameters of the calling function, of the function that is at the higher level. So we do not even need to give this parameter to this inner function. Okay, and we also don't need to provide it here. So this is also a valid code in JavaScript, and just for the proof, if this works, let's try it out. Load file. It still works. So this is This is just a JavaScript thing, doesn't have to do anything with recursion. I just wanted to show you that. Okay, as an exercise, I'd recommend you to write the Fibonacci function using a loop and compare your solution to the recursive implementation of the iterative algorithm we just did when we coded the fib2 function. Use a while loop instead of a for loop to see the similarities between these two implementations more clearly. This is the end of the video. I hope you liked it. I wish you all the best, have fun, happy coding, and see you next time.